this video, we will see how to calculate the standard electrode potential cell. So, in order to calculate the standard electrode potential cell, we can take a look of this equation where E naught cell is equals to E naught cathode and minus E naught anode. So in order to use this formula, we first need to identify in an electrochemical cell, we need to identify which one is the cathode, which one is the anode, and then we can calculate the E naught cell. So E naught cell also can be calculated using this formula, which is the E naught reduction plus E naught oxidation. Okay, for the oxidation in this cell, we can calculate that the E reduction for the oxidation is minus 0.76, while for the reduction is plus 0.34 volt. Okay, so when we want to calculate the E naught cell, we use the formula of E naught reduction cathode minus E naught reduction for anode, and we will get 0.34 minus negative 0.76, and we will get plus 1.10 volt. Okay, if you look at this diagram or figure, okay, this is a standard electrode potential table. So the one with the most positive value, which is the fluorine gas here, represent the strongest oxidizing agent. So it has the most positive reduction potential. And the bottom one, which is the lithium solid, so it is a strongest reducing agent and it has the most negative reduction potential. Okay, in an electrochemical cell, the greater the difference between the two, it will give you the greater voltage. For example, if you have copper and zinc here, so this is the difference between these two electrode, and this is the voltage resulted from the difference between these two. Okay, so you can do this practice using the formula to calculate the E naught cell. You can practice these two questions, and the answer the answer will be discussed during our next live session. Okay, how do we calculate free energy, and based on the free energy, how we determine the spontaneity of a redox reaction? So for a process carried out at a constant temperature and pressure, Gibbs free energy change is always equals to the maximum amount of work. So this is the Gibbs free energy change, which equals to the maximum amount of work. So W represent work. An electric charge will normally move from a point at high electric potential power, high electric potential power, to a point of low electric potential power. So the work needed to move an electric charge through a conductor depends on the total charge move and also the potential difference. So in other words, electrical work is also equals as charge times the potential difference. Okay, so the Gibbs free energy are normally represented by this SI unit of Joule J, which is also equals to coulombs times volt. And constant that are usually associated with this formula is Faraday constant, which is the magnitude of charge on 1 mole of electron, which equals to 9.65 times 10 to the power of 4 coulombs. Okay, and the maximum potential difference between the electrode of a voltaic cell is referred as EMF. Okay, this is the maximum amount of work or the free maximum potential difference, also we can regard as E cell. Okay, this is the not the standard one. The one that we have calculated before is the E cell. This is the standard when you have this kind of symbol. But when we want to calculate the potential difference in voltaic cell, it is using this symbol, which is the E cell without this node. And the maximum electric work of a voltaic cell for molar amount of reactant are usually represented in the following equation. Okay, in this equation, maximum amount of work is equals to minus n f E cell. So this n refer to the number of electrons, and then F refer to the Faraday constant, and E cell is refer to the EMF. And from above, delta G naught equals to minus n F E naught cell. If we want to relate delta G naught with the equilibrium constant, then delta G naught is equals to minus RT ln K. Therefore, minus NFE naught cell equals to minus RT ln K. And if we want to calculate the ln K, we can reorder the formula, and we will get NFE naught cell divided by RT. Please take note that the minus, both of the minus are now cancelled. So we substitute the value R and F at 25 degrees Celsius. So the term RT divided by F is 0.0257 volt. So finally, ln K is equal to NE naught cell divided by 0.0257 volt. Okay, so this represents the Gibbs free energy. So delta G equals to, if we have delta G naught, it is equals to minus NFE naught cell. And if the Gibbs free energy not for standard, so it is minus NFE cell without the standard symbol. Okay, so G meaning change in Gibbs free energy in joules. So N is number of moles of electron transferred, and F is the Faraday constant, and E is the cell potential. Okay, for a spontaneous redox reaction, there are some criteria. Okay, if we look at the delta G naught, so negative delta G naught will give a spontaneous reaction under standard state condition. Yeah. Okay, so if it is jet free energy is 0, so the reaction is at equilibrium. But if the delta G naught is positive, the reaction is non-spontaneous. Okay, so another important equation in this learning unit is the Nernst equation. So we will relate the ln K with the Gibbs free energy. So this has been explained in the previous slide. So in this case, delta G naught equals to minus NFE naught cell equals to minus RT ln K. So at the end of the reaction, what you will get is E naught cell equals to 0.0257 volt divided by N. This is the number of electron being transferred. Okay, times ln K. So this is a special case which relates concentration and cell potential. Okay, so E naught cell, you can use this equation, or if you want to use log, it will be different. This is the formula if you use log version. This is the formula if you use ln version. But both of the formula here show the relationship between the E node cell with the constant. Yeah. Okay. So this illustrates that electrochemical cells are a venue in which thermodynamics is readily evident. Okay, this is an example where we can use the Nernst equation to calculate the EMF or E cell. Yeah. Okay, so we have the concentration of the zinc solution. We also have the concentration of the sulfate solution, and also the copper solution, and also the next sulfate solution. So when we calculate the E cell, we use the formula of E naught cell minus 0.025 volt divided by N. So non-zinc 2 plus divided by copper 2 plus. So what we get is 1.1 volt minus this value. So we get the EMF of the cell equals to 1 volt. Okay, so please do the extra exercise that I have posted so that you can practice how to use this formula in your calculation.